Hi guys, today we're going to be talking about soeing PCR, which stands for splicing by overlap extension. If you don't know how basic PCR works, go look up another tutorial on YouTube and figure it out, because if you don't know how PCR works in its vanilla form, you're definitely not going to understand this soeing PCR. So soeing PCR, splicing by overlap extension. That means we're going to be joining, splicing, by overlap extension. So if we have two pieces of DNA, we'll say we have a fragment A and we have a fragment B. So A and B. And we want to go to a fragment A, B. So one fragment that has both of those in them, joined somehow. So the easy way to do this with soeing is through overlap extension. So all we're going to do is, if we start off with these fragments, we're just going to add a couple of extra bits to them. And these bits are really important. So I'm actually going to extend B a little bit. So we have A and B are totally different pieces of DNA, and they don't have any overlap or any homology. However, you can imagine that if we were to add a little bit of homology, so if we extended A, so A now had a little bit of B, so we'll put a little lowercase b there, and B maybe had a little bit of A, or maybe it doesn't even have a little bit of A, but you know, it could, we'll just, for this example, we'll pretend that it does. We're going to have a little homology region here. We're going to have a little zone right in between the junction where A and B share DNA with the other one. So A on its 3' is sharing some of its DNA with B, meaning that we have homology here. And B on its 5' is going to be sharing a little bit of homology on A's 3'. So I guess I'll, 5, 3, 3, 5. And when I talk about 5' and 3', I'm just talking about this number, the upper left-hand corner, or the upper right-hand corner, 5 and 3, 5 and 3. So now you can see that we have our fragment A, we have our fragment B, but we've added a little bit of B onto A and a little bit of A onto B. Let's not worry about how we get that for now, but just conceptually, we're going to pretend that we have this scenario. So if we were to put these together in a PCR pot, and we were to start boiling, or not boiling, but rather melting our DNA, so our PCR is going to go up in temperature until all of our DNA kind of melts apart. It all denatures. We're going to see that our fragment A is going to maybe, come apart. So let's see here. I'll try to redraw everything all denatured. So we have our fragment A. With its overlap with B. Here's a little lowercase b. Here's a 3', 5', and here's A. Sorry about the colors. Hopefully you can keep track of them. And 3 and 5. And I'm just going to draw a few base pairs there. So now we have one of our fragments has annealed, and you can imagine that the same thing that B has also annealed. And they're just kind of floating around. I'm not going to draw B quite yet, but you'll see why. And then we start to cool our DNA down so that everything starts to anneal. So we were denatured, we had a bunch of single-stranded DNA. Now we've cooled it down, and we might get a few, or a lot probably, A's are just annealing together, and some of our B's are probably also annealing together. But every now and again, we're going to get this homology region annealing to it, and that's why I was holding off on drawing. So we're going to get, our little homology zones annealing together. So we have our B, our big B, with its little a, And this is going to be the bottom strand. We have our 3' and our 5'. And it's kind of, here's our DNA. So now you can see that we've taken this strand. So let me change colors real quick. We've taken our strand A, our capital A, with our little b. We've taken that 5' to 3' fragment, and it's come down here as a single strand. And we've taken our big B bottom strand, which here I'll draw in the 5 and the 3', and that has come down right below it. And these two strands have annealed at this overlap region. So this overlap, we've gotten this kind of a hybrid thing where they didn't re-anneal to their fully complementary domain, but they've annealed only at this one region, this overlap region, in order to create this kind of partially single-stranded. So over here we have single-stranded DNA. Over here we have single-stranded DNA. And in our overlap, we just have this double-stranded overlap area. So that's overlap. And this will just stay here while we're doing annealing. Other things will be snapping together as well. We'll probably, as I said, get a lot of A's, or we're probably going to get a lot of B's that are going to be looking like their original form. But again, this is the special one right here. This is the one that we're interested in. So this is kind of the first step of sewing this is the overlap. And as the name suggests, we're going to be doing overlap extension. So when our temperature, so maybe we boiled and we annealed, or I'm sorry, we denatured at 95 and we annealed at 55, and then our temperature goes up to 72 for the extension, that's when the magic happens. At that point, our DNA, as we know, always extends from 5' to 3'. So this strand is going to start to grow in that direction until it runs out of template. And our bottom strand is going to grow in this direction until it runs out of template. So in this very first round, you can see that we had this overlap. So two different DNA fragments that share just a little bit of homology annealed at their overlap, and then we extended that overlap in order to create a new piece of DNA, so we were able to splice together A and B. And that's kind of just the first step, and after that we just have to amplify that. So in order to amplify it, what we would be doing, let me just grab a new color. Let's go with, how about green. In order to amplify this, we're just going to go and throw in some new oligos. So a forward oligo that binds to A, and reverse oligo that binds to B. And this will amplify the products of the reaction. So this forward oligo can only bind to the product, well, it can bind to anything on A, and on the big A, it will bind to the product, sure, I'll edit this part out. It will bind to the reverse complement fragment of the original A, and our reverse oligo will bind to the forward product of our B fragment. So they could potentially bind to our original templates up here, but they're not going to be able to create a chain reaction. They can only extend once in these original template fragments. They're just going to poop out there. There's no other oligos that are going to be going that way. But in our sewing by overlap extension case, they can amplify one another. So this guy is going to extend that way. Oops, that should have gone over. And this oligo is going to extend this way. So we've just doubled our product in our second step. And then from here, as you know, this is just a chain reaction that explodes. We're going to have more oligos that are going to be priming off of the products and the reactants from this reaction. and we're going to be getting more of these A's overlapping with the B's, joining together, annealing together to create more template for a soeing reaction to happen. And that's pretty much how the soeing reaction takes place. And I'll be back in a little bit to show the applications for soeing PCR.